Good afternoon, everyone. This webinar will last approximately 40 minutes. And at the end of it, we will have like a 5 minutes Q&A session. Okay, so welcome to everyone. Thank you for joining us today. I'm Benjamin Leblanc. I'm senior consultant at AC Energie. And I'm here with Louis Arnaud Pechna, also senior consultant at AC Energie. We are pleased to present this very topical topic, which is electrical boilers and their economic attractiveness, thanks to the flexibility revenues that they can generate. So before we dive into the topic, let me briefly introduce AC Energie. So for those who may not know us, we are composed of two departments, one consulting team, which Louis Arnaud and I are part of, and one financing team, mainly on the white certificate mechanism, C2E en français. So if we do like a slight focus on the consulting team, we support all kinds of companies in succeeding their decarbonization journey. And the main topic we can help you with are on that slide. So on energy sourcing, we can help you signing PPAs or purchase agreement, biogas purchase agreement, also design your market exposure strategy. Energetical excellence could be like group-wide programs of energy assessments. So and part investment strategy or the big investments in line with your decarbonization targets, like exactly e-boiler investment could be something we can analyze with you. And about the sustainability services, we can do like transition plans, climate reporting, value chain decarbonization. Of that kind of topics we can assist you here. Then, so after this quick introduction, here is the agenda for today. So we'll start with a brief context and then going on a focus on the e-boiler business case. Before going to important questions to be investigated, future perspectives, and then we'll finish with an executive summary with all of the main outcomes of this webinar. And after that, the question and answer session will start. I hope 5 minutes at the end. So for the context, so what we want you to see today is the hybridization of gas and power to produce steam for industrial companies. And by doing hybridization, we need to compare the gas and the electricity costs. So we did this analysis. On the left, you have like a specific week during February 2024 with the electricity price in blue and the gas price in dotted line, and the gas plus the CO2 price, which is the line above. And what we can see on this week, we can see that periods of time we have electricity which is cheaper than the gas, and if we add the CO2, we have more of the time when the electricity is cheaper. And if we do this analysis over the full year, we have the results on the right, with a very increasing trend over the past years, 13% in 2023 of time the electricity is cheaper than gas, which rise to 41% in 2024, and the first semester of 2025 is almost 50% of time electricity was cheaper than gas. So we will conduct this analysis over full 2025, but I think my feeling is the result will be quite the same, maybe above. So this is a first approach only on the prices of electricity and gas. So to go toward the e-boiler business case, we need to assess several technical factors like the yields of the boilers, the comparison between the gas yield and the electricity yield. Also to take into account the complete cost of energy when we add taxes and the charges network. But also operational issues like the ramp-up time. Do can we quickly respond to price signal? Do we have access to spots? What is the target of the client? Do they want to use the e-boilers most of the time, or just to use it when the electricity is cheaper than gas, etc.? We'll see all of these topics during this webinar. I think I let Louis-Arnaud take over for the next part.
Yeah, so we are gonna deep dive into the e-boiler business case. So talking about how we modelize it, then estimate the savings, discussing a bit about capex. Then we will have a focus on AFRR mechanism, which is a bit specific issues to flexibility assets. And finally, we are going to give you a bit of feedback on the different electric boiler projects we work on this summer. So to start with, when we discuss about arbitrage revenue, we have to build a merit order hour by hour or quarter by quarter to determine every hour what is the boiler which is most cost effective. So for example, on the left, we are on a day with probably a lot of renewable energy producing. So the electric cost is low, and the e-boiler is producing steam at a more interesting cost than the gas boiler. So boiler 1 and boiler 2 are gas boilers in this situation. And on the right, it's the opposite. The electricity is expensive. Consequently, it's more interesting to run with gas boilers. Due to this, the high volatility of electricity on the markets, the merit orders are it quite fluctuates a lot throughout the day. So if you want to capture the value of hybridization, you have to have assets that are quite responsive to adapt their charge to the merit order. That's a way to maximize the savings from hybridization. One other topic that I should talk about is here we are considering that our site is exposed to spot markets. That way we can gain the savings where when the price of electricity is low. So whenever you have built this merit order, you can modelize the gains throughout that you will make with your e-boiler. So the savings are modelized on different stream of revenue. So there's a lot of them. And to start with, on the left of the graph, you have the energy spent without an e-boiler. So if you are running with your gas boilers. And on the right, you have your energy spent, which is optimized. So running with an e-boiler when it's cheap to run with, and running with a gas boiler when the electricity price is high. Regarding the different stream of revenue, you have first the energy savings. That's linked to the fact that the e-boiler is more efficient than a gas boiler. You have revenue from AFRR, which is automatic frequency restoration reserve or secondary reserve. It's a flexibility market, and we will deep dive into this revenue stream later on. You have just to know the fact that you have two streams of revenue on AFRR, which are activation and capacity. We also have revenue from arbitrage. Basically, it's the fact that you capture some value playing with the markets. So working on electricity when it's cheaper, working on gas when it's more interesting. You also have another stream of revenue, which is MECAPA AOFD. That could generate substantial revenue, but there is a counterpart here, you have production constraints if you want to capture this revenue. Indeed, you cannot increase the gas consumption whenever you are activated on that market because it's a decarbonized mechanism. So it's just depends if you accept or not to reduce your production some day throughout the year. Then you also have the gains on ETS. So as an e-boiler is a decarbonized asset, you can gains on ETS emission. There is two important messages here. The first one is that the revenue model really depends on the energy cost structure, and it's also depends on if you have any additional constraint. So you have to build this modelization and this revenue split for each site you are working on. And another point is that there are extra sources of revenue, once again specific to each site, that could be considered. We can think about indirect compensation, ETS2, and shop rebates. And yeah, really the message here is that it's really specific to each site. Yeah, and here we have a good example. So it was a site where we could reduce the energy spend from approximately 2/3. So that's quite significant. So we have talked about revenue. Let's talk a bit about CapEx. What's important regarding CapEx is that it's divided in three main parts. So the first one is the boiler parts that include boiler and water treatment. There is also the electrical works. That's quite a significant part of the CapEx, and at least the energy and engineering, and construction. Regarding the boiler cost, it's quite fixed. It's increased very slowly with the boiler power. So you have a really good interest into maximizing the size of your boiler. Also because it will bring you more value on the revenue stream. And of course, you have electrical connection constraints. That's why you will be limited into maximizing the size of your equipment. So you have to investigate the cost of an electrical connection with Energie or RTE. One last point on CapEx. There is also possibility to get third-party investment. So some suppliers propose this kind of investment model. If you cannot support the investment, it's really interesting to deep dive into third-party investment, especially because what they usually propose is to align the electricity steam price with the gas steam price and share the extra revenue that will be made thanks to AFR, spread, etc. What we would suggest to work on that stream, the CapEx stream, is to start discussing with suppliers to get offers and a good idea of the CapEx that this kind of project needs. After that, we have talked about CapEx. Let's switch to subsidies. There are two main mechanisms that you could apply to get some subsidies. The first one is the white certificate, so in French, C2E. There is no standardized operation yet, so C2E is working on it. But if you apply to a specific operation, you could gain approximately 5 to 10% of the capex in C2E. And regarding decarb and decarb flash, so there are two mechanisms depending on the size of the project. But What's important here is that the decarb and non-decarb flash could cover until 40% of the initial capex, including white certificates. So you have to investigate that point. It's really a massive subsidy that you have to work on. After that, I will let Benjamin deep dive into AFR mechanism.
Yeah, thank you. So let's take a closer look on the AFR. So this mechanism here, this is to understand how it works. So what it's important here, you have to be very quick to respond to the TSO, to RTE in France. You have like 5 minutes to react for the flexible power you offer. If you have been selected, you have 5 minutes to react and to go to the power needed. And then after that, during this period of time, you have to follow a 4-second signal. So every 4 seconds, RTE is giving you a power to adjust your power. And then at the end of when your offer is not selected anymore, you have 5 minutes more to go back to the initial power before this operation. And in terms of about the economic system, this is a bidding system. So all the actors make offers with opportunity costs, and then these bids are over each 15 minutes for the AFR. Yeah, so if you want to go toward that direction with hybridization project and an e-boiler, you have to check the flexibility requirements to achieve this ramp up from minimal power to the nominal power within the 5 minutes. You have to consider this, the network feasibility, also the gas boiler's capacity to compensate, because if you reduce the electricity consumption of e-boilers, for example, you have to compensate with the gas boiler during the same period of time to get this the steam production you need. So then the next slide, this also focus on AFR. The AFR is composed of two components, the AFR up. So up because we want the grid frequency to be increased. So up or down is for the frequency. So if you want to increase the frequency, you have to decrease the electricity consumption. And so in our case of hybridization, you have to compensate with the last gas boiler in the merit order. So you have to consume more gas, CO2, and taxes because you decreased the e-boiler consumption. With the AFR down, this is the opposite. You want the grid frequency to be decreased. So you want the electricity consumption to be increased. And so you save the last gas boiler in the merit order. So you save gas, CO2, and taxes. So in terms of modeling, you have these two very important inequalities. You want to trigger the AFR up if the gain from the AFR up and the gain from the TURP is higher than the cost, in that case, using the gas and CO2 of the last boiler. I insist here, we have the CO2. This is in case the industrial company is on the EU ETS system. So they have to pay the CO2 and also consume the gas. For AFR down, the inequality is right there. The gains are you avoid the last boiler, you avoid gas, you avoid CO2 price, but you have to pay AFR down and the TURP. And so if these two inequalities are correct, you can trigger the AFR. So I've seen a question concerning the TURP and the AFR. So for the TURP, the TURP is calculated on the real consumption going to your plant. So if you are using AFR down, you increase your electricity consumption. So you have to pay the TURP for this amount of electricity through AFR. But if you reduce the steam consumption with the electricity consumption with AFR up, you save this TURP amount. And a very specific technical information here, but there is no dependence with the electricity cost of the customer, because RTE neutralized the volumes exchanged with the AFR. So the impact of AFR is not visible at the supplier level. But for the tube, this is different because they look at the real consumption toward your plant. And concerning the savings of AFR, there are two kinds of savings: capacity savings associated with availability of the piece of equipment. This is in K euro per megawatt hour you make available. And then the second stream is the activation part, again associated with the energy you modulated with via AFR. This is in euro per megawatt hour modulated. Okay, then we wanted to show you some feedbacks on the previous project we had with clients in the recent months. So here we have three examples here with inorganic chemistry, petrochemical, and two examples in petrochemical. In terms of context, they wanted to replace one gas boiler and adding e-boiler with very favorable cost structure, with tube abatement extra. And then for the power, it was a range 10 or 15 megawatt. We keep like a range for confidentiality. I mean, for the capex, something quite important, between 4 and 9 million euro before subsidies, but the payback were very good, around 2 years, with an implementation in 2028. And the production of steam, with our modeling, we got like between 20 and 30% of steam produced from the e-boilers, so quite a significant amount. So going with a lot of CO2 reduction, between 35 and 40% of reduction of CO2. For the second example, it was the payback was a bit higher, but steam production also a bit lower, between 10 and 15% of steam production from the e-boiler, but also quite important percentage of CO2 decarbonization. Would be quite a challenge for the site with a gas boiler. It's always difficult to reduce this CO2. For the third example, it was a boiler like less powerful, between 2 and 5 megawatts, more between 2 and 3 megawatts. And the payback was not as good because in that case they get like steam from a steam supplier from the plant just next to them. So this steam supply at very cheap cost decrease the potential of the e-boiler, and in that case is not as good as in the previous project. So one thing to keep in mind is always dependent of the specific site you are analyzing. That's why it's important to do specific modeling for each site with a merit order depending on your cost structure, your steam production, etc.
So after investigating the economic part, we will deep dive into the technical part bits. So the first one is just what are the different technology for e-boilers that exist. So there are 4 of them mainly. The 3 first one are electrode boilers. So the first one is a jet boiler. The second one is the immersed electrode boilers. And this one is double tank boiler. This last one is an immersed resistance boiler. So there is no electrode, it's the resistance. And the real difference between electrode boiler and resistance boiler is on the power available. So above 5 megawatts, you will work on electrode boiler, and below 5 megawatts, you will work on resistance boiler. Between 1 and 5 megawatts, you can investigate both electrode and immersed and resistance boiler. But if you are above 5 megawatts, this is just not cost effective at all. So if we deep dive a bit into the operational parts, to produce steam here, you will have a water reservoir here in yellow, and with little holes. and you will put water in this reservoir that will make some water jet here from the reservoir to the electrode. This will connect both, and electricity will pass from the electrode to the center here, the reservoir. As electricity passes through the water, there will be Joule effect, and you will produce heat, so steam. There is also electricity here from the electrode to the counter electrode here that also produce steam. You will adjust the level of production of steam with the level of water inside the reservoir. You have different way to do that. So you can use a pump to adjust the level, or just will mask some holes to reduce the number of holes that are producing jets. For immersed electrode boiler, you have the 3 electrodes inside the boiler that are directly immersed, and the electricity will pass through the water, so from the electrode to the water to the boiler tank that is neutral usually, and that way you will have electricity passing through water and producing heat once again. To adjust the level of production here, you will adjust this mask that will mask a part of the electrode. Yeah, a part of the electrode. Regarding the double tank boiler, here you have quite the same principle as here, but inside a little tank inside the boiler. And you will here adjust the level inside the internal tank to adjust the production of steam. Finally, the immersed resistant boiler is just electrical resistance that are inside the water and that are heating the water. What you have to know here is that there is different characteristic of each boiler. So, for example, regarding the conductivity inside the boiler, jet boiler, allow to run at high conductivity. Immersed boiler like low conductivity, and the double tank boiler is working at very low conductivity. So this will make constraint on the water treatment. If you have high purity water on site, you can investigate working on that topic. If you have to build everything from the beginning to the end, it might be interesting to work on jet boilers. There is also another aspect that is important, is the quality of steam produced. So here you have low quality steam. That means that it's saturated steam, and here you can produce overheated steam. I won't go deeper into that topic. What's important to keep in mind is that investigating this is really important. So we recommend to discuss with different constructors to see what's more adapted to your sites. If we additionally, we have other technical aspect that we have to discuss, and I will try to go fast on that one. So the first part is safety. So as any industrial project, safety is the main topic. So sometimes you will need to add additional costs to make physical production, etc. But globally, it's an equipment that's quite safe. Regarding the boiler technology, I've already discussed about it. Regarding the water treatment, so what I recommend is to work on both topics, boiler technology and water treatment at the same time. Regarding electricity, three technical aspects that you have to investigate. First is the power connection. What we recommend is to maximize the power that you can install, so the power of the e-boiler you can install. It will allow you to increase some revenue stream, but there is constraint, of course, regarding the electricity connection available. So you might just make an analysis to see the optimum between gain and capex. Regarding the supply voltage, so e-boiler can work from 6 to 36 kilovolts. What we recommend is to work with voltage you already have on site. And usually it will be 20 kilovolt, which is the typical value. Regarding the neutral regime, it's a bit complicated topic, but basically this could be summarized like that. So the necessity of having a transformer to change the neutral regime or to protect the network will we have to be investigated regarding two things. First, safety issues, and second, selectivity issues to protect the rest of the site from the electrical boiler. We can deep dive into that topic with you if you want to. Do not hesitate to ask us.
I think we're going to rush a bit because we have quite a few slides ahead. So here, just to say, it's essential to take a step back from these very good economic results by conducting sensitivity analysis. They are very, very essential in that kind of exercise. Here's what we did with three parameters: the capex of the e-boiler, the gas price, and the percentage of time favorable to the electricity. So the percentage of time when electricity is cheaper than gas, with unfavorable assumptions, the baseline assumption, and favorable assumptions. And when we look at the results, we see the difference in IRR, so internal rate of return. We have for the capex, the difference between unfavorable and favorable is not as big, between 30% to 47%. For the gas price, the spread is higher, between 3% and 53%. And then if we look at the time the electricity is cheaper than gas, we could have like negative IRR and a very good IRR. So this is not the values which are important here. It's only the way we need a sensitivity analysis on that kind of exercise, and the IRR is very, very volatile. So there's a high spread between the different, depending on the assumptions we take. So the management should, IRR on this kind of projects are very good, but management should be aligned with this kind of risk, and this risk should be on the table. After that, very quickly, so there is e-boilers is not the only solution to decarbonize the steam production. There are other technologies like the geothermal energy, solar thermal, the biomass, the solid recovered fuel boiler, the high temperature heat pump, or even BPAs. All of these technologies have like advantages, but also drawbacks. Mainly, I think I will move on because we want to focus on the e-boiler, but this is not the only solution. And so we connected the analysis on the IRR of the project and also on CO2 abatement cost on the different technologies. And what we can see here, there is e-boiler has very good IRR, but very depending on the assumptions we take on the energy cost structure, on the IFR revenues, on all of kind of this. We don't have the assumption here. It's only, again, not the value which are important, but the difference between the different scenarios. So yeah, comparing different technologies is something you could be be doing, because e-boiler is not the only solution on that. And the next slide is on a very specific technology, which is electrothermal energy storage, which is innovative solutions to push steam decarbonization further by maximizing electrical power and utilization. I mean, this is you have like resistances here using grid electricity, and you store this heat into this kind of container. And then at the end of the container, you have a heat exchanger for your heat usage, or the steam, high pressure steam, or hot air. So you are decorrelated the electricity consumption and the steam production. You can decorrelate these two. By doing so, you can charge during more time during renewable production hours, and then store this heat and discharge when you need it. And this solution has quite the same technical performances of e-boiler. You have these same power capabilities. Efficiency is a bit lower than an e-boiler, but above 95%. You can also make use of the same revenue streams as e-boiler, but you can go a bit higher in terms of decarbonization of your steam because you have a higher annual utilization rate. You can make a bigger capacity because you can store the heat, so you can put a bigger capacity. And in terms of financing, capex a bit higher, so the payback is a bit longer, but savings are bigger with more decarbonized steam products. So this information could come from APIR. So thanks to them for sharing it, and please feel free to contact them if you have any questions concerning this technology. Renaud?
Yeah, if we go and look at the future perspective, so I would like to be really careful in the fact we do not have any crystal ball, so it's just we're gonna discuss about drivers, but we do not have any certainty. So first thing first, on renewable production. So we expect in Europe, we expect that the production mix will be more oriented to renewable energy. And we have also observed a correlation between renewable energy into the mix and spread. So if you increase renewable energy into the mix, you will increase spread. So if you increase electricity spread, then you should have it should be favorable for the spread revenue. Also on the right, so the European Commission expects the need of flexibility to increase a lot. It's mainly due to the fact that we will have more renewable, and that's also favorable for the flexibility revenue availability on the long term, on the mid and long term. So if we switch to another driver, we have the ETS price, which is also expected to increase. So here we have consolidated forecast from experts, and as you can see, the ETS price is increasing from 7 to 12% per year. Once again, it's not the number that's important, it's more the trend. Yeah, and this should also be positive for arbitrage, because if the CO2 cost is more expensive, that means producing steam with gas boiler is more expensive and is favorable to electricity production. I won't deep dive into the main drivers, but feel free to contact us if you want to deep dive into that topic. I think what's more important is here, the projection of revenue for an e-boiler. It's important to do that because of if you launch an e-boiler project, it won't be installed tomorrow. It needs time to be installed. So you have to take into account that the revenue will decrease rapidly, especially on the AFRR capacity. So it's expected to decrease at approximately 20% per year for the next 5 years. Why that? It's mainly because as the market has been liberalized recently, there is not enough capacity working on that market yet. But there will be a lot of assets that will work on it in the future years, for example, battery or e-boiler, etc. So it will reduce that revenue stream. But at the same time, the spread revenue should increase as there is more and more renewable on the market. ETS revenue cost will also increase, and the last point I would mention here is 2 points. Sorry, the OPEX and maintenance costs for e-boiler are quite the same for gas boiler. There is not much difference in terms of amounts. And finally, the flexibility operator fee could be high it's usually a part of the revenue made in capacity and AFRR, sorry, AFRR and spread revenue. And finally, here you will find an executive summary that could be interesting for you to have an overview of the presentation.
And I hope this session has been helpful and informative. If any questions come to mind later, feel free to reach out. We're pleased to answer you. And thank you again for joining us.
Thanks a lot, everybody.
Great rest of your day, and see you. Bye bye.
Have a nice afternoon. See you.